Hello, and welcome back to my Minecraft computer. So, I know it's been a really long time since the last time I posted anything about it, and that's because it's been a really long time since I've done anything with it. I just haven't really had time and hadn't completely forgotten about it, but um, there were a lot of other things that just ended up being more important. So, where I left off, I had built the ALU. So this has the ability to do addition, subtraction as well with that, bitwise and or not, shift left and shift right. And I explained more deeply about that in a previous video. It has two inputs for these. It has, I labeled them as RS1 and RS2. That's register source 1 and register source 2. We'll get more to that in a bit. And there is a control unit here, or part of a control unit, it's not completely finished yet, that takes 4 inputs in binary, 4 bits, and that code then selects which of these, which output from which of these operations will go on to the next step. So that's what all of this is. And then there's this part. This is where there's been some progress. So I've done a little bit here and there, and this is the new part that I have not covered yet. So that's what we're going to focus on right now. So first of all, we'll start over here, and then we'll work our way back towards the other stuff. These are the registers. So the way many computers work, actually probably most CPUs work, is that they have a set of registers inside the CPU. And basically, this is the memory that the CPU has. And there's usually not a lot of it. So for mine, I only have 16. So each one of these is a memory slot that's numbered here, 0 through 15. And each one holds 16 bits because this is a 16-bit computer. And that is represented by whether or not there is a redstone brick in that spot. So right here, so if we go to like this one, actually let's go to this one as an example. This is a 0, this is a 0, this is a 0, because there are no redstone blocks sitting on those copper blocks. If we go to like one here, this is a 1, this is a 1, this is a 1, and so on. The rest of that we'll get to in a second. So all of this serves as the memory of the CPU. If you need something that takes more memory than that, which most computers do, then what it does is it pulls from a slightly farther set of memory, slightly farther away set of memory that has more storage. And those are called caches, and there's different levels of those. But basically, the idea is the smaller the amount of storage, the faster it can run, because it doesn't have to send signals as far, and it doesn't have to search through as many things. So the idea is to prioritize having the most used things in the smallest possible and closest memory storage. So the registers is the smallest possible and the closest memory storage. I don't know at this point if I will add any caching or anything to this, because I'm more doing this for fun. I don't really care if it runs like real programs or not. And that's just a lot of work. So we'll see. But this is enough to run some like simple mathematical, I don't know, some algorithms for fun. So the way that this works, a note about a change that I made to the design philosophy of this is that I realized I was not going to get it finished in any reasonable amount of time because of the amount of time that I have to work on it if I was actually running basically physical wires everywhere like this. So I decided to switch approaches. So for the rest of it, what I will do is have command blocks that just set a redstone block in a different place. So the command blocks are not contributing to the logic of the computer at all. All of the actual logic and all of the actual data storage and everything will be done using like normal redstone. All that these do is just like sets a block. I don't know why I did fill and not set block. Oh, actually I know why I did that, because this fills them in a column. But by doing it this way, by doing it this way, it will save a lot of time, and I don't really consider it cheating in my opinion because it's not contributing to the logic at all. And at some point, maybe I'll go back and fill in all of the redstone wires between everything. But this is more just for the fun of it anyway, so it's not really meant to be the most efficient or the most like ideal necessarily. So that's the decision that I made. So when information comes from the ALU, it comes through here, and over here, the control unit, like I mentioned, controls which of these operations, which output gets sent to the storage. So this part here, all of these blocks, these will get, if this has a redstone block, it's actually not implemented fully yet. Some of this is still not fully implemented. But what will happen is there will be another control signal that controls whether or not information is saved. Because not every operation will save something in memory. Sometimes we're just loading a different instruction, or we do an instruction that doesn't necessarily have an output. So if we have an output, there will be a special signal that will allow the output through. In this mess of things here, this controls where and which register it saves the output to. So each of these columns here sends the output to a different register. And all of this logic before this decides which register that output gets saved to. And that gets controlled by this. So if we take some redstone here, let's say we want to save this in the 6th place, the 6th register. So that would be this, because that's 6 in binary, 0, 1, 1, 0. So as you can see here, it filled in all of these redstone blocks, these columns in different places. What that's doing is it's basically blocking the different signals to different places in this tree so that it only is going to allow the signal to get through and go to the 6th one. So this should be 0, 1, 2, 3, 4, 5, 6. So it should be allowing the signal through to here, I believe. Well, maybe not. I have not touched this in a while, so I'm going to have to double check where I left off and make sure that everything is fully implemented, because stuff may not be fully implemented correctly yet. Once it gets saved, however, we can come over here to one of the registers, and we can see that there's a lot of stuff going on around this. So we have this set of command blocks here, we've got another one over here, and we've got another one up top. And all of these signals are blocked by these bone blocks. Why bone blocks? I don't know. But what's going on here with this is that these are the 3 outputs, basically. These are as if these wires are connected to the register source 1 and register source 2 that we had over there going into the ALU. Those, as well as we'll have another register source, basically, that will be for reading the instruction. And that's controlled by these. So if we place something here, that will replace, that will allow this signal through. And then if we power this here, that will put that back. And allowing that signal through will set the value that was in memory here to the register that was over here. So as you can see, since that was all 1s, we get all 1s over here. And so that is how my wiring system works, just because it's a lot faster. But effectively, it's the same as if instead of command blocks, we had actual just redstone lines running all the way over there. Effectively, that's what it's doing. So by allowing that through, by setting that, we can load a specific register into either one of the 2 memory slots, or one of the 2 inputs for our ALU, or we can load it in as an instruction. But the instruction part isn't built yet. Not completely. Some of it is. Part of it is there. But I also had to figure out what were we going to do with output for like showing the user? So I decided that the 0 register, the first register, so to speak, will be our display. So anytime you want to display an output, you just save it to this register. So this register, you notice it doesn't have the copper blocks underneath. Instead, it has more pistons. So if we go under here, you can see that there are pistons and then there's more redstone down here, and that moves these into place to transfer that memory into this display. So whatever is in register 0 is what we see in the display. There's also an error bit, and there is a command where you can set the error bit to true or set it to false, and that's how we'll catch errors and display errors. So for example, if you're dividing by 0, then you'd have to check in the code whether you're dividing by 0, and if you are, then you can throw an error. Basically, we can set that error and then just stop. So that's what our output will look like. For programming it, and this is not fully implemented yet, but for programming it, we'll have something like this, where we'll have another view, and these should be levers, not buttons. But basically, you'll enter in the number that you want to save, you'll enter in the address that you want to save it at, and then you'll click either save or clear or one of the different options. And then you can add that number very easily into the register. And that's how you'll program it, because this stores both commands and numbers. Because commands are actually just numbers. That's all that they are. We'll get to that in another video, actually, that I'll be putting out at some point fairly soon. Because I've written some software on the side to help make the translation easier into the binary code for this. But that's what I have so far. So the progress is slow, but a lot is already here. So if we can now actually look at kind of the overall flow of how the computer should work. So the main thing that's missing is the control unit needs to be expanded a little bit so it can fully read an input and know what to do with it. Then it will send that based off of the instruction, it will choose 2 different registers potentially, send them through the ALU, send that result to another register, and then there will be a clock, which I think I'm going to put the logic for that over here, because the clock is going to have some memory to know what register we're on. And the way that will work is it'll keep track starting at 1. I'm going to have it start at 1 because 0 is our display, so that's always going to be a number, not a command. So we'll start at 1. Our first command should start at 1. And every command it runs, after that command gets done, it'll move on to command number 2, and so on. Unless you specifically use an instruction that tells it to go to a different instruction, in which case it'll pick up from that point and continue on, adding 1 each time. When it gets to the end, it'll just restart from the beginning, because mathematically and architecturally that is much easier to implement. So, and that's pretty normal for how computers actually work. That's how things get stuck in infinite loops. So, that is what I have so far. There has been some progress made, but maybe not a lot.